Okay, this is about take 712 of the part 5 of lesson 8.7, volumes, cross-sections, squares, and rectangles. In this video, we're going to show you a couple of examples with more complicated functions than what we showed you when we were trying to teach you what we're doing here. We'll start with this one and look at these two functions, f of x and g of x. F of x a cubic polynomial and g of x a quadratic. And we're going to find the volume of the solid with a base that's defined by the region bound by the curves g of x and f of x. The cross sections are perpendicular to the x-axis and the cross sections are squares. Go to calculator and I've got this graphed, and this is the cubic function. This is the quadratic function. These intersect at points 1 and 3 on the x-axis. We'll zoom in a little bit on that. I'm going to change the window to, let's do x equals 0 to 7, and let's do y equals -7 to 3. So we can see a little better what that looks like. So this is the region that we're looking at, the boundary. And the cross sections are going to be perpendicular to the x-axis. And so the length of them is going to be the top curve minus the bottom curve and the width. We're going to sketch that on our board so we can make some drawings here. So quadratic and the cubic to look like this. Our rectangles, our base, our cross sections are going to be perpendicular to the x-axis. So I'm going to draw one rectangle with width dx. The length of that rectangle is going to be the quadratic g of x minus the cubic f of x, top curve minus bottom curve, right? Oops. Top curve minus bottom curve. So I'm going to pull that out. Oh, back to draw. I'm going to pull that out. And I'm going to draw one of the cross sections. This side is g of x minus f of x. The height is g of x minus f of x because they're square cross sections, meaning the length and width is the same, or the height and length is the same. And then the width of this cross section is dx, so that the volume of one cross section is g of x minus f of x times g of x minus f of x, which could also be written as g of x minus f of x squared times the width dx. That's the volume of one cross section. Remember, we looked at the calculator and said this intersects at 1 and 3 on the x-axis. So if we want to sum the infinite number of rectangles and cross sections that make up this region, we're going to do the integral from 1 to 3 of g of x minus f of x all squared times dx. A lot of times on the free response questions, you'll be asked to just set up the integral and not solve it. That's what we've done here. If you had g of x and f of x defined and you put this in right, this would be sufficient to get credit if you were asked to set up the integral but not solve it. Now we're going to go ahead and solve it on the calculator. And I'm going to show you how to, the calculator on my computer is not got the new operating system. So you know that when we do math and 9, that's the integral function on the calculator. And when you do that, gotta get to the draw again. When you do math 9 on your calculator, it gives you an integral symbol with a box here for your limits of integration, and then it gives you a box here that you put in your function for, And then it gives you a D and another box for you to put the variable we're integrating with respect to. So when you bring that up in your calculator, you put your limits of integration in those boxes. In here, because this is a quantity squared, you're going to have to add a set of parentheses. It's going to show up with a set of parentheses, but you're going to have to add another one. So it will look like this when you do it. Well, it'll look like two sets of parentheses. And if you've got this stored in y1 and y2, I have g of x is y2 in my calculator and f of x is y1. So I'm going to go to the y vars menu. Let me show you that. So y equals, yes. All right, so I'm doing the quadratic minus that thing. So I'll go to vars, scroll over, it says vars, function, and do y2. Scroll down to y2, hit enter, and that will, that's not what I want to do there, but for this function. But that's how you get your y2. So what I'm going to enter in the calculator here for my integral is y2 minus y1, get the y1 out of the y vars also, then squared, and then close it, the parentheses will be closed. That's what it will look like inside that box there. Then you go here and put your x in to have it integrate. So when we do this on the calculator, it will look like, if I have y2 as g of x, 1 to 3, and it will look like y2 minus y1. If you type in y1 and y, if you write y1 and y2 on your test booklet, you have to define those somewhere. They have to be defined as g of x and f of x. This would have been sufficient for your free response question to set up, but this is what you would type in a calculator. You can't leave it like this. You do it in a calculator unless you have y1 and y2 defined. But I'm going to go ahead and find that on the calculator. So I can quit. From 1 to 3, oops. And there's parentheses opening up. I'm going to add a set of parentheses because I know I'm going to be squaring this quantity. y2 minus y1, close parentheses squared, and come out and put my variable integration in x, and it comes up to 38.552. And whatever your units are, if you're doing this on free response, they would be cubed. And that's how we do difference when we have a region bounded by two curves and a square cross section. We're going to do one now where we have a region bounded by curves and it's going to be perpendicular to the y-axis, and we're going to do a rectangle. So this one, find the volume of the solid with the base defined by the region bound by the x-axis, the curve g of x and f of x, whose cross sections are perpendicular to the y-axis and are 3 units taller than they are long. So this time I have a quadratic. Just going to draw. And this one we know is x minus 3 times x minus 1. We can factor that. So we know it intersects the x-axis at 3 and 1. And it's a quadratic, so it comes down like this. And then we have the function x minus 1. So x minus 1 hits at -1. It has slope 1, so it goes up like this. This time, I don't think I defined it in this problem, but we're going to do it in the first quadrant. How about that? In the first quadrant. Region in the first quadrant. So what we're looking for is the solid that is generated, or its base is this region in this first quadrant here. I'll make a better rectangle than that. But the rectangles are going to be perpendicular to the y-axis. And so this is x, and this is y. But we're going to have to integrate with respect to y in this case, because our rectangle is perpendicular to the y-axis. So, like I've done before, I'm going to reflect this across the line y equal x so that I invert my x and y axis, which is going to make, if we do that, let's see where that's going to go. That's going to turn this, where this is 1, and this is 3. And then we're going to have to figure out where this point is. And this is going to be the region I'm working with now. So I'm going to go ahead and draw that's right. Oh, sorry, my bad. I was confusing myself. This is what I'm going to be looking at, perpendicular to the y-axis. This is my rectangle. I was letting myself get confused there. So that's my rectangle. All right. And now I need to figure out what this y value is. And to do that, I'm going to set these two functions equal to each other, x minus 1, and solve so I can get both points of intersection. I know one of them is going to be at y equals 1. When I subtract x from both sides, I get x squared minus 5x. And when I add 1 to both sides, I get plus 4. So this is going to be x minus 4 times x minus 1. And so this intersection is going to occur where x equals 4, but I need to find out the y value when x equals 4. And we can do that by plugging in either one of these. F of 4 equals 4 minus 1 or 3. So that means that when x is 4, y is 3. So this y value is going to be 3. So since I'm looking for this, working with this region here, my integral will be set up from 0 to 3 and integrating with respect to y. So now we just need to figure out what this quadrant, what these cross sections are going to look like. So I have the volume of a single cross section. I need to draw the cross section. The width of the cross section is dy. The height or the length of the cross section is going to be, let's see here. We need to solve these for y, don't we? We do need to solve these for y before we can do this, because it's going to be the quadratic minus the linear. So we need to take f of x, which is y equals x minus 1. Solve that for x. When I add 1 to both sides, I get x equals y plus 1. And then we'll solve the g of x. So this one's going to be a little more involved because it's y equals x squared minus 4x plus 3. I'm going to have to complete the square on this to solve this. I need this to be a perfect square binomial on the quadratic side. So I'm going to go ahead and subtract 3 from both sides. Get y minus 3 equals x squared minus 4x. We completed the square earlier this year, and we knew that we took half of this and squared it. Half of negative 4 is negative 2, plus square that, we get plus 4. That's what we put on both sides. So I end up with y plus 1 equals x minus 2 squared. Take the square root of that. I get plus or minus the square root of y plus 1 equals x minus 2. So that x equals 2 plus or minus square root of y plus 1. That is my x for my quadratic part, except for because we got the top half of that curve, it's just going to be plus. I doubt you'll have to do one like this, but it's fun. So now we've got to figure out what exactly it is that we're going to integrate. Let's look at the cross section, and we need to figure out what this height of that is. So here, I'm going to take, I don't know why I keep doing that, one rectangle, and this one has, the rectangle is 3 units taller than it is long. So if this is the length, this is dy, the width, the length is how tall this is right here. So that's going to be the quadratic 2 plus the square root of y plus 1 minus the linear, which is going to be y plus 1. And so let's simplify that. It becomes the square root of y plus 1 minus y, and then 2 minus 1 is 1, so plus 1. So that's the height or the length of that rectangle. Let's go ahead and make this the cross section. And so it says that the rectangle is 3 units taller than it is long. So if this is this dimension, then this dimension is going to be 3 units taller, or the square root of y plus 1 minus y plus 4 when I add 3. So the volume of one of those is going to equal this dimension. It's going to be kind of crazy. Square root of y plus 1 minus y plus 1 times this dimension, square root of y plus 1 minus y plus 4 times dy. That's going to be the volume of one of those. And so we're going to integrate those from y equals 0 to 3 to get this. Oops, just the part on the right side of the y-axis, or the x-axis. Well, I did it again, but that region there. So let me erase my little dy here. And let's put in this integral symbol. The volume of one of these, y plus 1, square root of y plus 1, minus y plus 1 times the square root of y plus 1 minus y plus 4 times dy. And that's the integral we need to integrate in order to find the volume of this solid. So I'm going to type that in the calculator and see what that looks like. I'm sure it's going to be fun. We're going to go from y equals 0 to y equals, oops. Remember, when you're doing this in your calculator, we're going to replace the y's with x's. I'm going to again put parentheses in because I've got parentheses inside there. So I'm putting parentheses inside of parentheses. Square root of x plus 1 outside the square root minus x plus 1. Then close parentheses, open parentheses, square root of x plus 1 minus x, and then plus 4. And then close parentheses, and then again, I'm rewriting the calculator. This is not calculator syntax. This is just the integral we're setting up with respect to y. But if you're going to do this in a calculator, you have to replace all of these variables with x because the calculator won't understand y. And that gives me, if I had to evaluate it, 13.866. Remember, we can chop or round. It's safe to chop because you can't make mistakes if you chop. And this is going to be units cubed. That was a fun problem. I don't think you'll see anything that complicated on the exam, but it's fun to know how to do those. And that is how we work these types of problems.